Okay, so welcome everyone. This is our third deep learning seminar of the year. And today we're honored to have two speakers. Dr. Saber Jafarpour is an assistant professor at the University of Colorado Boulder, and Alexander Davydov is a graduate student at the University of California. And today they will be talking about non-Euclidean monotone operator theory and applications, and robust implicit networks via non-Euclidean contractions. So after you.
Okay, perfect. Let me share a screen. Can you guys see my screen? Can you see the slides?
Yes.
Oh, okay.
Okay, perfect.
Okay, great. Okay, thank you so much for inviting us. This is a pleasure to giving a talk in your seminar. My name is Saber, and I am a research assistant prof at University of Colorado Boulder. And this is actually a joint work with Sasha. Both of us had taken some parts of it and developed a different aspect of it. And now we are presenting it on different aspects of this work. So let me start by saying that, as we all know, learning algorithms have become very popular, and we are seeing an increase in deployment of them in autonomous systems, in our environment, in our societies. And this is mainly due to the increase in the availability of the data and also increase in computational power of our learning models. However, these models are known to be extremely fragile with respect to their input perturbation. An instance of this fragility in machine learning have been studied under the name of adversarial perturbation, where a very small change in the input of a learning model can lead to a very large change in their output. And as you can see, for example, even a very small changes in the pixel of an image, which is not detectable even by human eye, can lead a state-of-the-art learning algorithm to classify the image in an incorrect way. So ensuring robustness of these learning algorithm as a result is very important, and this is particularly more important in safety critical environment and safety critical applications where the error in the learning algorithm can lead to some safety dangers or disasters. So let me introduce robustness of this learning algorithm in a more mathematically way. Any questions? No, okay. So given a learning algorithm and some input perturbation on the input of the learning algorithm, we say that the learning algorithm is robust if the image of that input perturbation under the learning algorithm doesn't go into unsafe set, which is something that is already predefined. For example, it can be misclassified labels, or it can be some output which is large enough, which is not acceptable for safety of the people or the system itself. And this notion of robustness actually raises two questions for learning algorithm. The first question is that given a learning algorithm, how can we check it if it is robust? And the other question, this is called the question of verification. And the other question is question of training, that how can we design learning algorithms that are robust and satisfy these properties? So as we all know, learning algorithms can be large dimensional and have nonlinear component. So computing the exact value of their output under the input perturbation can be very complicated and challenging. As a result, one approach which has been proposed in the literature is to over-approximate the image of neural network or learning algorithm under this input perturbation and check the safety of that over-approximation. And one notion which plays a critical role in this type of over-approximation is the notion of Lipschitz bound. So given a learning algorithm, a Lipschitz bound is bounding the changes in the output and connecting it to the changes in the input, right? So it provides an upper bound on the changes to the output with respect to the changes in the input. And as you can see, the Lipschitz bound of learning algorithms, as this definition suggests, it depends on the norm for sure. Using this Lipschitz bound, of course, we can over-approximate over the output of the learning algorithm, and as a result, provide a way for ensuring robustness of these learning algorithm. And that works like this. If you apply the learning algorithm on a ball, which is the norm ball of starting from some point U with radius r, then it should be included in the ball centered at NU and radius r lib, right? As you can see, this is the ball. Then the output of the ball, the exact output of the ball would be this shape, which is a little bit different. But what we can ensure is that the ball which is coming from the Lipschitz bound, it contains our real image under the input perturbation. Okay, perfect. So this also shows that the smaller the Lipschitz bound of the neural network, the more robust they are, because then we can ensure that this set is smaller, and as a result, the neural network are in a safer region, right? Okay. So in the literature, actually, Lipschitz bound have been studied extensively to study robustness of neural networks. It has been shown that some architectures of neural networks, such as feedforward neural nets, finding the exact value of Lipschitz bound for them is NP hard, and as a result, several different algorithms have been proposed in the literature to estimate Lipschitz bound. What we are going to do in this talk is that we are going to use monotone operator theory, which is a mathematical framework, to estimate Lipschitz bound of learning algorithms, right? Okay, so let me open a parenthesis here. This parenthesis is a little bit of a theoretical parenthesis. I will introduce you what is the monotone operator theory, and I will present some of the results, that theoretical result we got there, and then I will go back to learning algorithm, and we will see how these results are being applied for studying robustness of learning algorithms. Okay, so monotone operator theory is a classical framework in functional analysis that studies operators on Hilbert space. So what is a Hilbert space? A Hilbert space is a space equipped with an inner product which is complete under that inner product, right? Then we say an operator is monotone if it satisfies this inequality, and it's strongly monotone with the parameter m, it is satisfied a much stronger inequality like this. The study of monotone operator dates back to 1960, where Minty and Browder studied these operators for PDEs and ordinary differential equation. Rockefeller studied extended these notions to optimization, and more recently, Combet and Bausche and Boyd and Ryu also studied this problem, these type of operators for optimization algorithms. And monotone operators appear in many applications. One prevalent example of that is in optimization, when you want to minimize a function over some domain, and you can show that convexity of that function is equivalent to monotonicity of its gradient. In dynamical system, monotone operators also appear a lot. And if you consider dynamical system x dot equals f of x, you can show that contractivity of that dynamics, meaning that the trajectory of the dynamic converging to each other with respect to L2 norm is closely connected with monotonicity, strong monotonicity of the vector field minus f. As a result, and there are more and more applications of these monotone operators in different areas of math and applications. And however, one of the properties of these operators, which makes it very interesting for us, and I will explain later why this is an interesting property, is the following classical result, which I would like to call it Minty-Browder theorem, but it's a little bit more stronger than that. And I think Tasha will explain what is Minty-Browder. It's a little bit more detailed and more subtle than this. But the theorem states like this. If you have a strongly monotone operator with respect to an inner product, let's assume H for now is Rn. Our Hilbert space is Rn, and we equip it with standard inner product on Rn. Then for if f is a monotone operator, a strongly monotone operator means that satisfying this, then we can show that f has a unique 0, x star, and that unique 0 of f can be computed using the average iteration for theta is small enough, right? So this is the result, essentially. This is one of the main results in monotone operator theory, and this is the result that we are going to use here. And essentially what this means is that monotone operators have this nice property that the average iteration is always contracting and converges to their unique 0. Right? Perfect. Okay, so right. So let me introduce another notion, and this notion plays a critical role in our development of theoretical development of non-Euclidean contraction theory, and this is the notion of logarithmic norm. So given a matrix A and a norm, we define the logarithmic norm of matrix A using this limit. So you can consider this limit as directional derivative of the matrix norm with respect to at point identity with respect to direction A. Right? And it turns out that for certain classes of norms, like L2, L1, and L infinity, you can find very nice closed form expression for this logarithmic norm. And in the literature, this notion has been studied under different names, like one-sided Lipschitz constant or matrix measure. But the importance of this logarithmic norm for us is that we can show that we can characterize monotonicity and also strong monotonicity using logarithmic norm with respect to L2 of the Jacobian of the operator. This is a very interesting result. The reason is that this allows us to extend the classical monotone operator theory, which is defined on Hilbert spaces and for inner product, to Banach spaces and norms, right? So as a result, instead of defining F to be monotone, because this is a if and only if condition, we can say mu2 of minus df is less than or equal to 0, and that gives us a necessary and sufficient condition for monotonicity. Now, if we want to extend this to non-Euclidean norms, we can define non-monotone operators with respect to non-Euclidean norms like this. Let this be a norm on Rn. Then an operator is called monotone with respect to this norm if it satisfies this condition. Logarithmic norm of minus df is negative. And if it's strongly monotone, if logarithmic norm of minus df is less than minus m with some parameter, right? Perfect. So essentially, this notion of logarithmic norms was very useful for us because it allowed us to generalize this monotone operator theory to a much more general framework that we can now, instead of working with Hilbert space, we can work on general norm Banach spaces with arbitrary norm, right? And it turns out that the same exact theorem that I mentioned in the beginning for monotone operator theories hold for non-Euclidean monotone operators too. So if F is a strongly monotone operator with respect to a norm, it also has a unique equilibrium point, and this equilibrium point can also be computed using average iteration, right? Okay, perfect. So I think here I'm going to close that parenthesis, mathematical parenthesis. And what I'm going to do is that I'm going to go back to the learning part, and I am going to study and use these monotone operator, non-Euclidean monotone operator theory that we developed here to study learning algorithms. Okay, so let me start by the model, the learning model that we're considering. Here we're considering a special learning model. It's called implicit neural networks. So what are implicit neural networks? Implicit neural networks are a class of neural networks which are defined using an implicit equation. So if you want to compare them with feedforward neural network, for feedforward neural network, an input enters the neural network, and then it goes through hidden layers and it gives you an output. And all of these are iterative equations, input layer 1, layer 2, layer 3 to y, right? However, for implicit neural networks, the story is a bit different. So their input and the hidden layer are defined in an implicit way through a fixed point equation like this. And then the output would be a linear combination of the hidden layer, right? So this class of neural networks called implicit neural network because they are defined using an implicit fixed point equation. And it has been shown that they contain feedforward neural net, ResNets, and many other class of architectures of neural networks as a special case. And in here, I'm assuming that phi are activation function, and let's assume that the activation functions are monotone and they are slope restricted, means that they satisfy this type of inequality. So essentially, you can consider this implicit neural network as a general, in a much more general framework where the notion of layer is defined implicitly as a function of input. And this type of neural networks exists in machine learning, for example. And when you have a differential equation instead of the layers, then we call them neural ODEs, or sometimes you have optimization problem instead of layer, different type of neural networks. And here instead we have fixed point equations. So the origin of this implicit neural network goes back to the work of Coulter and Colton and El Gavi and his collaborators. They call these implicit neural networks, different things, and but essentially the idea is the same, that the layers are defined implicitly using a fixed point. And it has been shown that these class of neural networks have a lot of advantages compared to traditional feedforward neural networks. For example, as I mentioned, they contain feedforward. So in terms of representation, they are a richer class of learning algorithms. It has been shown that on certain problems such as differential equations, certain optimization problem, they have shown better performance compared to traditional neural networks. And compared to a neural feedforward or traditional neural network with the same accuracy, they have shown a better memory efficiency. Okay. So, however, there are a couple of challenges in studying them. First of all, their hidden layers are defined as an implicit fixed point equation. So the first question that arises is that, does this fixed point equation has a solution? And we call this the well-posedness of this learning algorithms. And are they well posed? Does this fixed point equation has a solution? Because if it doesn't have a solution, then my neural network is useless, right? And then, of course, after we study well-posedness, we are interested in studying robustness, as I mentioned in the beginning of this talk. We want to understand how input-output behavior of this system is and how robust it is, right? Okay. So the key insight that we have for studying this type of implicit neural networks is that let's consider this fixed point equation as an operator, and let's consider this operator x minus phi a x plus bu plus b. And as a result, fixed point of this fixed point equation are going to be zeros of this operator. And robustness would be sensitivity of the solution of this operators, zeros of this operator with respect to u, which is a parameter here, input parameter, right? Now this allows us to use all the tools from non-Euclidean monotone theory that we developed and to study robustness and well-posedness of these implicit neural networks. So in particular, the key result that we got is that if we assume that logarithmic norm of matrix A with respect to infinity norm is less than 1, then this NU operator that I defined is going to be a monotone operator with respect to L infinity norm. And as a result, we can use this Minty-Browder classical theorem to show that it has a unique solution, and the solution can be computed using average iteration. And using that average iteration, we can also get this incremental bound on the input for different, on the hidden layer for different inputs, right? We can bound this incremental distance between fixed point of different inputs by the difference between the inputs, right? And as a result, we can use this condition 3 to find a Lipschitz bound of this neural network as follows. We want to find a Lipschitz bound from u to y. It's equal to Lipschitz bound from u to x star times the Lipschitz bound from x star to u. So u to x star, this is what we got here. And x star to y is exactly norm of c. So essentially what we get is that the Lipschitz bound from u to y of our neural network is given by this expression, which is a simple expression to compute, and we can compute it very easily, right? Okay, any questions so far about this type of neural network? So here, using the non-Euclidean monotone operator theory that we developed in this talk, we could study well-posedness, provide a condition, this condition for well-posedness, and provide a bound for Lipschitz bound of input-output Lipschitz bound of these networks. Okay, so now let's see how we can do training of these neural networks to make them more robust. So actually, let's assume we have a loss function, we have some training data. Then what we can do is that we can train these neural networks like normal. The only thing is that at every, we have to impose this condition of fixed point because the hidden layer are obtained using a fixed point. And in order to promote robustness, what we can do is that we can add a regularizer term, lambda Lipschitz of u to y, and then we add this condition mu infinity of a being less than gamma. Gamma is a number less than 1 to ensure that our model is well posed, right? So this is how we train these neural networks. And then we solve this optimization problem, training optimization problem using a stochastic gradient descent. Okay. Okay, so we have applied this result to the MNIST dataset, and the results for different value of lambda are here. And we compared it with 2 different approaches that exist in the literature for training implicit neural networks. This MON is actually the work of Coulter and Colton, and IDL is the work of El-Gavi. And what you can see is that with almost the same accuracy, our training algorithm gives us order of magnitude better Lipschitz bound compared to the existing ones in the literature, which are these two. And these are ours. And as you can see, as we increase lambda, which is the regularization factor, well, our error is going to increase, of course, but our Lipschitz bound are getting smaller. So there is a kind of a trade-off between this robustness and accuracy of our models. We also can show empirical robustness of our neural networks over some type of attack to these neural networks. So here we consider the inversion attack, which is defined like this. This is an attack which doesn't depend on the model of neural network. It's independent of the model, and it only perturbs each pixel, each input, by epsilon times the sign of that pixel minus 1/2 everywhere 1/2, right? And as this is this attack on different epsilon, as you can see here. And again, this is the plot of the accuracy based on the L-infinity amplitude of the perturbation epsilon. And as you can see, again, these are the models in the literature. These are our models for different value of lambda. And as you can see, our models, although they have lost a little bit of accuracy in the clean performance, meaning if there is no perturbation, their accuracy is lower. However, when the perturbation is larger, the accuracy of our models are much, the robustness of our model are better, so their accuracy are much better. So again, here you can see the trade-off between this clean performance and robustness in the way we train our neural network. So in conclusion, we extended the idea of monotone operators to non-Euclidean monotone operators on normed spaces using the notion of logarithmic norm. Then we used non-Euclidean contraction theory to study, or non-Euclidean monotone operator theory to study well-posedness of these implicit neural networks. And then we found Lipschitz bound of these implicit neural networks using this theory. So I think that's my part. I think I would like to give the floor to Sasha to continue, because his talk is a little bit more detailed and he has a better explanation of all the procedures there. So with that, I will stop here. And yeah, Sasha, please continue.
Sure. Thank you, Saber. I'm going to share my screen right now. Okay. Hopefully everyone can see that okay. So this is going to be part 2 of the talk. Thank you, Saber, for introducing a lot of the notions that I'm going to now talk about moving forward. And thank you again, everyone, for inviting both of us here. So in this part of the talk, I'm going to go into a little bit more detail on the non-Euclidean monotone operator, like the theoretical aspects, and then I'm going to show some more applications to the implicit neural network closer to the end. So again, this was joint work with Saber and our co-authors, Anton and Francesco. So I'm going to first provide like a little bit, there's going to be a little bit of repeat information. Hopefully that'll help instill some of the concepts. So kind of as, again, like a little bit of background on the standard monotone operator theory. We can consider an operator A, which is going to be now a set-valued operator from a Hilbert space to itself. And we'll say it's monotone with some parameter m greater than or equals 0 if this inequality holds. So you have this inner product u minus v into x minus y should be greater than or equal m times that norm x minus y squared. And the inner product and the norm are coming from the Hilbert space. And then u and v are just elements of that set-valued output of that operator A. So this is it's a standard definition. It seems a little esoteric, but at the same time, this is, like Saber mentioned, fairly classical. If you have a convex function, which is perhaps not differentiable, its subgradient satisfies an inequality like this. So in the case that m is equal to 0, we'll say it's monotone. In the case that m is strictly positive, you can call this operator strongly monotone. And in the monotone operator literature, there are two quote-unquote like prototypical problems that people study. And those are kind of something like an inclusion problem, or essentially find the 0 of the operator A, or a splitting problem, where one tries to find a 0 of a sum of two monotone operators without directly invoking the sum of the two. Somehow you want to like you can evaluate somehow maybe A nicely and B nicely in some way, but jointly evaluating A plus B is challenging. So find a zero of this sum. And by now, there's actually a lot of really excellent results in the literature on solving inclusion problems and splitting problems. And largely, these results are based upon either Banach contractions or Krasnozelsky-Mann iterations. So essentially, contraction iterations or non-expansive mapping iterations in some sense. For the inclusion problem, this is something like the forward step method or kind of those average iterations Saber introduced. It could be the proximal point algorithm, which is really useful when your operator is set valued and you cannot directly, you can't iterate a set in very easily to find a fixed point. And then for the splitting problems, you have something like the forward-backward splitting method or the Piesman-Rackford splitting method. And for a really nice primer on these sets of tools, Ryu and Boyd wrote an excellent survey paper in 2016. And anyone interested in the classical monotone operator theory who's not familiar, strongly encourage them to read that paper. So why monotone operators? They've seen a lot of success in a lot of different fields. I'm listing just a few of them here. In optimization and control, like I mentioned, the subdifferential of a convex function is monotone. In game theory, oftentimes finding a Nash equilibrium can be posed as finding a zero of some pseudo-gradient operator. In systems analysis, you can study input-output behavior, also from the viewpoint of monotonicity. This is something like incremental passivity. And maybe what's of most interest is in machine learning. These monotone operator tools have been used to develop new architectures and new and better understanding of somehow like equilibrium behavior of neural networks. And by now, there are two really excellent textbooks on the subject by Bauschke and Combet and by Ryu and Yin on using these tools, both on a more theoretical side and kind of on the more application convex optimization side. So this is kind of the traditional monotone operator theory. So I think Saber did a pretty good job already introducing why we would want to go to the non-Euclidean setting. But let me kind of give even more examples, perhaps. And that's really that like a lot of problems of interest are better stated in Banach spaces or in finite dimensional norm spaces equipped with non-Euclidean norms. Kind of like the prototypical example, the one that Saber introduced, is this like L-infinity robustness analysis of neural networks. A lot of times it makes a lot of sense to study L-infinity robustness rather than just the standard two-norm robustness. It's easy maybe to quantify like how much an adversary can change each pixel rather than quantify like how much energy an adversary can put into an attack. So in this regard, an L-infinity Lipschitz constant makes a lot of sense. In systems analysis, big L-infinity norm analysis is something related to bounded input, bounded output systems and can be useful to study from this perspective. Within theoretical reinforcement learning, we have value and policy iterations to find, optimal policies. These iterations are well known to be L-infinity norm contractions, which are really, intimately closely tied to somehow like these monotone operator methods. And I think a better understanding there would be very useful. And, as of yet, the tools are not really there to bring this fixed point iteration into the framework of understanding it from a non-Euclidean monotone operator setting. And then last and certainly not least, in distributed optimization with delays, oftentimes convexity or strong convexity of your objective function is not sufficient to guarantee convergence, and you actually need stronger conditions, something like L-infinity contractivity. So motivated by these four examples, we were kind of interested in taking like the classical monotone operator theory, extending it to the non-Euclidean case, and then seeing what we can do with it, essentially, hoping to bring it to bear. Now, this is a big ask to extend the whole framework from Hilbert to general Banach. So in this talk, I'll show you what we can do for finite dimensional spaces equipped with non-Euclidean norms. And then, there are open questions still about going even beyond that. So like Saber mentioned, the key tool is really the logarithmic norm, which I'll introduce again, just, to hope that it sinks in. It has this limit definition, which can be kind of, you can view it as a directional derivative of this matrix norm in the direction of A. And it admits simple expressions for the norms that are most commonly used, the two norm, one norm, infinity norm, and in some other cases, you can evaluate it as well. It has a lot of nice properties, some of which I've listed here, but there are many others that are of interest. So subadditivity and positive homogeneity means that the logarithmic norm is convex. And then if you can evaluate this logarithmic norm, it for free gives you some bounds on all the eigenvalues of your matrix A. So then going to the actual non-Euclidean monotone operator framework, this is the definition that Saber gave. If your F is differentiable, we'll say it's strongly monotone or just monotone with parameter M with respect to a norm, if this inequality holds. So this, you might complain to me, Sasha, this is only for differentiable F. In the Hilbert case, you can do, non-smooth, set valued, whatever. And I will tell you, okay, that's a reasonable complaint. But it turns out you can do the same thing. You can do something similar when F is not differentiable. You just have a much more complicated expression. So I'm just going to say, like, under the hood, these things will work even when F is not differentiable, but we still need some continuity. So let's get rid of this formula because it's a little bit hard to look at. And kind of most interest is going to be the case where F is going to be strongly monotone with respect to an L1 norm or an L infinity norm, perhaps scaled by some diagonal weights eta. So the usual one norm is the sum of absolute values. When it's weighted by a diagonal matrix eta, we just scale each entry according to that entry eta I. And the level sets of this norm look something like axis-aligned diamonds, perhaps with some aspect ratio. The infinity norm is similar, where again, we just scale each of these absolute values by 1 over eta, and then you get axis-aligned rectangles. So going forward, I'm going to focus specifically on these norms because the constants become nicer. But in the paper, we studied the much more general, like arbitrary norm case, and you can do the exact same analysis. And if you're interested in the details for general norms, I encourage you to read the paper. So two key tools within monotone operator theory are something called the resolvent and the reflected resolvent of your monotone operator F. So the resolvent is defined like so. If you have your mapping F and some parameter alpha greater than 0, you take identity plus alpha F, and that mapping inverse is called a resolvent. And the reflected resolvent is something similar. You just take twice the resolvent and then you subtract identity. In monotone operator theory, it's interesting to study these objects because even for set valued F, these like fixed points of these operators correspond to zeros of your original monotone operator. And the same is true even in the non-Euclidean case, because these objects are defined independently of any norm. I can give you an arbitrary map F, and then I can tell you what the resolvent is. But the one thing is, there's this inverse, so it's not clear in general if this resolvent even it exists or on what domain it exists. And in monotone operator theory, there's a classic result, the Minty-Browder theorem, that tells you that these objects exist when F are monotone. And in our paper, we extended the Minty-Browder theorem to the non-Euclidean case. So in that case, if F is continuous and monotone, then these have full domain, these operators, the resolvent and the reflected resolvent, which really mean that, okay, this inverse is well-defined. So you don't have to worry then about perhaps like iterating these maps. You don't worry about them leaving their domain. So really, you can then go ahead and iterate these operators, this resolvent or reflected resolvent, to try to find zeros of the original monotone operator. So we want to iterate these maps, but it's only useful to iterate these maps if they're non-expansive or if they're contractive. And kind of the nice key, one of the key results really is that we can fully characterize the Lipschitz constants of these objects. So if you have the resolvent of a monotone F, which is monotone with respect to some diagonally weighted L1 or L infinity norm, the resolvent has a very simple Lipschitz constant. It's 1 over 1 plus alpha m for any alpha you pick. So when your operator or when your mapping is monotone but not strongly monotone, it's always non-expansive. If you're strongly monotone, then you're always contractive. And for the reflected resolvent, the story is a little bit similar. You have a nice characterization of the Lipschitz constant, but it's only true for alpha small enough. And small enough is dictated by, essentially how large any of the diagonal elements of your Jacobian can get. So this is a small difference compared to the traditional monotone operator theory, where the reflected resolvent is always at least non-expansive. So this is one key difference between the traditional theory and this one. So, okay, we want to iterate these maps. So let me show you two different iterations for a monotone inclusion problem. We have a continuous monotone F, and we want to find a zero of it. The forward step method is essentially the average iterations, or you just do identity minus alpha f, you take a forward step in the direction of your monotone operator. This is something like gradient descent if f is the gradient of a convex function. And if your operator or your mapping f is strongly monotone, you get linear convergence provided you pick your step size properly. And in the case that you're not monotone, or that you're not strongly monotone, but you're just normal monotone, as long as the set of zeros of your mapping f is not empty, then you're guaranteed to converge to an element of the set of zeros with some, asymptotic rate. And this is actually a big difference between the non-Euclidean theory and the Euclidean theory. This item 2, the case of monotone but not strongly monotone, this method will not converge in the general monotone, like the Hilbert framework. Whereas if you're monotone with respect to an L1 or an L infinity norm, this iteration will converge. So, okay, going beyond the forward step method, you can look at the proximal point method, which is really the iteration of the resolvent mapping. And again, you have similar convergence results where if you're strongly monotone, you converge linearly for any alpha like step size that you pick. And if you're monotone but not strongly monotone, you converge sublinearly to some element of the set of zeros, provided it's not empty. And actually, we can characterize, the different convergence rates for these algorithms in the cases of being monotone with respect to like a L2 norm, a classic Euclidean norm, or with respect to a diagonally weighted L1 or L infinity norm as a function of the alpha that you pick and the parameters M and L, which are the monotonicity and the Lipschitz constants of those mappings. So here in this left column, we have the results like standard in the literature. And then these on the right are kind of tailored to the framework when you're diagonally weighted, you're monotone with respect to diagonally weighted L1 or L infinity norm. And what you can see actually is that these optimal Lipschitz constants are smaller in general than the corresponding estimates that you get if you were monotone with respect to an L2 norm. It's a little bit complicated to make a direct comparison because, monotonicity coefficients and Lipschitz constants do depend on the norm. But in general, like if you can establish that you're monotone with respect to diagonally weighted L1 or L infinity, you may be able to take larger ranges of step sizes for your iterations. The Cayley method, I didn't introduce it, but this is simply just iterating the reflected resolvent. Okay, so let's move on to splitting problems, where we now have F and G, and maybe one of them is kind of complicated to evaluate, so I need to access it only through its resolvent. In that case, you can use either forward-backward splitting or Piesman-Rackford. And again, you have the same like general convergence results that you would get in the standard monotone operator theory in the non-Euclidean case. Forward-backward splitting looks like this. You take a forward step in F and then a backward step in G through its resolvent. And if both F and G are monotone, if F is strongly monotone, you get linear convergence. And if F is merely monotone and G is monotone, then again, you get this sublinear convergence result, provided that the set of zeros is not empty. Piesman-Rackford is similar. You have a little bit of a more complicated looking iteration, but if you're strongly monotone, you have linear convergence. And then I got tired of writing the same thing over and over, but again, if you're monotone but not strongly monotone, you converge sublinearly. Okay, so I've finished introducing all the, most of the theoretical results. Let me kind of comment on the case of set-valued inclusions. So one critique would be that everything that you showed is for continuous mappings, not set-valued. And what I would say is, well, we can work out a special set-valued case. That case is the following. Suppose you want to solve this inclusion problem, where F is now monotone with respect to an L1 or L infinity norm, and then G is separable like so, and it's convex, closed, and proper. So in general, this partial G is now set valued, and we want to solve it. We want to find the zero. The key tool first is understanding the proximal operator of a closed, convex, and proper mapping G. Its proximal operator is defined like so. And for closed, convex, proper G, it's always well-defined, this proximal operator. And kind of drawing the connection to everything I introduced for monotone operators, the proximal operator of this convex, closed, proper G is just equal to the resolvent of its subdifferential. So this is a well-known result going back to Rockefeller. And this kind of hints maybe at, we can look at the resolvent of this, like partial G, in terms of the prox. And then maybe we can say some properties about the prox in the case of the non-Euclidean norms. And the answer and the main result essentially is that if you have closed convex proper and separable in this way, G, and some parameter alpha greater than 0, then both the prox and like the reflected prox or the reflected resolvent version of the subdifferential are always non-expansive with respect to L1 and L infinity norms. And this is a very nice result that actually directly lets us apply, forward-backward splitting, Piesman-Rackford splitting to this problem in order to find a 0 of this, set-valued inclusion, even when F is monotone with respect to an L1 or L infinity norm. So as the application, we have the implicit neural network, which Saber already introduced, so I'm not going to go into too much detail. It's defined using this fixed point equation. Phi is diagonal. Its nonlinearity acts element-wise, and each phi I is going to have slope between D and 1, where D is perhaps 0 or it's positive but less than 1. So this is a little bit, you can get sharper rates a little bit if you let D be different from 0. So a sufficient condition for well-posedness is what Saber mentioned. The logarithmic norm of A is less than 1. I'm going to call it gamma for convenience because it's going to be useful to get convergence rates. And in that case, this is the previous result. X minus that, that phi of AX, so on, is strongly monotone with respect to the L infinity norm. And one can apply the forward step method or the average iterations in order to compute that fixed point. And it converges for every alpha in a particular range, and you have this linear convergence rate. And this is exactly what we did in our NeurIPS paper. But one interesting extension, actually, is that you don't need to view this fixed point computation just as a monotone inclusion problem. You can view it actually as a monotone splitting problem. And the key theorem, essentially, is that finding an equilibrium point or a fixed point is equivalent to this monotone splitting problem, where F is affine, and G is some sum of convex closed proper functions, such that the prox of G is equal to the nonlinearity appearing in the neural network. And you might complain to me, say, Sasha, I have no idea what such a GI looks like or if it even exists. And I would say that's a very fair complaint. But there's a really nice result coming from monotone operator theory, an equivalence result by Bauschke and Combet, that says that a scalar function phi I is the proximal operator of some convex closed proper GI, if and only if this condition holds, which is exactly our slope restricted condition where maybe I let there be a D here, but still I'm guaranteed for sure that there exists some GI for which the prox is equal to that nonlinearity. So somehow this problem of finding the fixed point is exactly equivalent to finding the 0 of this monotone splitting problem. And from there, you can directly apply forward-backward splitting or Piesman-Rackford splitting, find the ranges of step sizes, and get convergence rates that are strictly better. Well, they're at least no worse than the rates of convergence that come from the average iterations or the forward step method. So here's a simple, numerical example. We just generated a random matrix A, made sure that we bounded its logarithmic norm either by 0.9 or -1. We tried different activation functions, leaky ReLU or ReLU, and then we checked the convergence rate for each of these iterations. In the case that you had a positive logarithmic norm for A, actually forward step and forward backward splitting directly fall on top of one another. You actually can see that their convergence rate is equal, whereas Piesman-Rackford is faster. You can see the convergence rate is faster in that case. Like you can see it coming out of the math. In the case that your logarithmic norm bound on A is negative, actually forward backward splitting is always outperforming forward step method, either for leaky ReLU or for ReLU. And then Piesman-Rackford again is converging faster. And something else that's interesting to notice is actually when your logarithmic norm is more negative, somehow like your operator splitting problem is more strongly monotone. So it takes you fewer iterations to actually get closer and closer to the fixed point. Okay, so I showed you how you can use this monotone splitting framework to understand and compute fixed points. How about going beyond fixed point computation? Let's talk about robustness again, which Saber very generously introduced already, motivated. So under that assumption, this well-posedness assumption, you can define, again, this map, which computes the fixed point of your implicit neural network. Then an upper bound is actually going to be this induced norm of B divided by 1 minus gamma. And I didn't write an output equation here, y equals c x plus c. If there were an output equation, you could multiply this by induced norm of c. And the proof is really actually the consequence of looking at the forward-backward splitting iterations and unrolling them, and then taking the limit as the number of iterations goes to infinity. So really, this bound is actually a direct consequence of the splitting perspective, rather than just looking at the monotonicity directly of that x minus this. So somehow like this, you gain something by viewing it from the splitting perspective. And then what Saber showed in the previous half of the talk was that the Lipschitz bound you get like directly otherwise is actually it's a little bit worse. So you get something which is the same, but you now have this max of gamma and 0. So really taking the monotone splitting approach really gains you flexibility, and actually it kind of, using this new perspective, it tells you that you can regulate robustness just by tuning gamma. Essentially, you can make it negative and make your Lipschitz bound smaller. Whereas if you work with this bound, it's not clear that using gamma more negative will actually improve your Lipschitz estimate at all. So this was an improvement that we had from our previous work, like going forward with this this framework. Okay, so that's all the technical stuff I wanted to talk about. Let me begin to wrap up. So in summary, we provided a transcription for monotone operator theory toward finite dimensional norm spaces with non-Euclidean norms. We showed provable convergence of like standard iterative methods in monotone operator theory in this case. And then I showed how you can apply these tools to fixed point computation and the robustness of implicit neural networks by estimating Lipschitz constants. And then kind of going forward, I think there are a lot of interesting extensions that can come from this work. I think the infinite dimensional Banach space setting is really interesting. I think it can provide new insights. And then kind of even staying in the finite dimensional realm, I think the set valued case is really important and really interesting. I showed you a very special case when you had convex closed proper separable functions that we can say something there, but I think the full general case is not yet worked out. And I think viewing value iteration as a non-Euclidean monotone splitting problem is an interesting avenue. I've looked at it a little bit, but I don't have any conclusive answers yet. I wonder if that can gain somehow, you can gain new insights into what the value iteration is actually doing if you view it from this perspective. And then I think there are tons of potential applications to optimization and neural networks that are still, as of yet, to be explored. And then, just to wrap up, I'd like to thank all the collaborators on this work, Saber, Anton, Francesco. And then these were the two papers that this talk was based off of. I strongly encourage you to read these two if anything I said was of interest. And yeah, I'd like to open the floor to any questions.
Okay, so thanks for the great talk. And are there any questions from the audience? Okay, so I have one question for both of you. And so, Sasha, can you go back to the page where you mentioned the convergence rate for the algorithm?
Like this one maybe, or
No, the one before this.
like these ones. Okay.
Yeah, okay. So you mentioned that okay, so my question is, if we know that f has more regularity, say f is C infinity or analytic, then can we have better convergence rate in this second or both situation here?
That is a good question. That's not something that I've thought about. And yeah, the answer is probably due to the fact that like we structured this approach so similarly to that which is done in the standard monotone operator approach. In those settings, like these objects f are not super regular, all things considered. And I think it's in the case that f has much more regularity, it may be possible, but I'm not sure. I don't know, Saber, do you have any more insights on that?
Well, I think I have I have one. I don't know. That's a great question, but I think there are some results that might be related to this. For instance, I think they probably are related to the structure of the zeros of f and how they converge to it. Because if, for example, we know that if I know that the contraction theory literature much better. And in contraction theory literature, if you have a dynamical system, which is weakly contracting, minus df is monotone, and it's real analytic, then you can show that the forward step method always converges to an equilibrium point.
Yes.
Right. So I think real analyticity there is important, and it gives you some rate. But I'm having a little bit hard time connecting it with what we have here. But that's an excellent question, I think. I know that there are some results about real analyticity helping, because essentially, if a function is real analytic, it's the structure of its zeros cannot be very arbitrary. Right? We know that zeros of real analytic functions, they are not, they're disjoint. Then I think that we can say something. I'm not sure how far we can go, or can we get extremely better result, but I think there's some of, especially real analyticity, I think is going to help a little bit.
Yeah, it's a good insight. I mean, just to comment a little bit more, actually, like on these like point 2, like these are results that essentially we're invoking the theory of non-expansive operators in Banach spaces. So convergence of Krasnozelsky-Mann iterations. They, in general, do not assume very much structure beyond, non-expansiveness. And the rate that we get is somehow worst case rate. It might be possible, like Saber mentioned, but yeah, I don't know. It's worth looking into, perhaps.
Okay, so thank you, Sasha. And I have another question for Dr. Jafarpour. So can you go back to your page 10 of your slides?
Oh, my talk. Okay.
Yeah.
Yeah.
Sorry, I put it on the other side. Okay. Page 10. Yes.
Yes. So here you mentioned before that computing the Lipschitz constant of function or network is NP hard, but here you're adding this regularizing term lambda times Lipschitz u to y. So how do you actually implement this in?
Oh, actually,
Yeah.
I'm using the formula that I obtained above. I'm using this formula, and this is not the exact Lipschitz bound. This is an upper bound on the Lipschitz bound. So essentially, we are saying we cannot compute it exactly. This is exactly Lipschitz of FNN that Sasha has, with some extra C. But maybe I should have said that this is an upper bound on Lip. Sometimes I use Lip as all of the Lipschitz bound, but this is not the exact. That's a good question. Maybe a little bit of bad notation from my side. This is not the exact Lipschitz bound. It's an upper bound on the Lipschitz bound. And then as a result, we are just putting that number here, exactly the norm infinity. Does that make sense?
Yes.
Yes, of course. I think Sasha got a better result in terms of finding the Lipschitz. So for example, my Lipschitz has this maximum here. This plus sign means this is a maximum of this guy and 0. So if we apply Sasha's result there, I think we will hopefully get better training. Because my Lipschitz is not as good as the Lipschitz that Sasha has.
Okay, so any other questions from the audience? Okay, then thanks again for both of you for giving this great talk. And yeah, I will see all of you next week. So thanks everyone for coming.
Thank you so
See
much
you.
for having us both.
Yeah,
Thank you.
for
Bye.